Hello, hello. Let's start yet another devlog. Yesterday I reached to exercise number 61. I'm going to continue this. Yeah, let's start. This one is about coercions. It'll only take us a moment to learn the Zig type coercion rules because they are quite logical. Types can always be made more restrictive. Yeah, var foo, this is not restrictive at all, right? And then here we have a pointer to foo, which we are assigning to p1, and here we have a const pointer, meaning this pointer cannot change the value. And then but the p2 can point to something else as well. So this is mutable. This part is immutable. Numeric types can coerce to larger types. Yeah. Float widening, integer widening. Yeah. Single item pointers to array, coerce to slices, and many item pointers. Single item pointers can coerce to many items pointers. So we put a star here, and we have a many item pointer to this. Single item mutable pointers can coerce to a single item pointers pointing to an array of length 1. Once more, single item mutable pointers can coerce to a single item pointer pointing to an array of length 1. So this is one integer. We are making a pointer, but we are creating a single item array. Okay, why is this even useful? Payload types and null coerce to optionals. Payload types and error coerce to error unions. I don't get why it's called payload type. By payload type, do they mean this value? Yeah, probably, because this is what is being set as optional. Or is it? I think this is what it's setting to optional, and then you can set it to null as well. Yeah, this is the payload type then. Payload types and errors coerce to error unions. Const my error. Undefined coerces to any type, or it wouldn't work. Yeah. Compile time numbers coerce to a compatible type. Just about every single exercise program has had an example of this, but a full and proper explanation is coming your way soon in a third eye-opening subject of Comptime. Okay. Tagged unions coerce to current tagged enum. Enums coerce to a tagged union when that tagged build is zero length type that has only one value, like void. 0-bit types like void can be coerced into a single item pointers. The last three are fairly esoteric, but you're more than welcome to read more about them in the official Zig language documentation and write your own experiments. I need to get back to this as well. 061 coercions. Okay, we have the print statement. Here is letter. Your type, your type here must coerce from add letter, a pointer, which is a star U8. Use coercion rules 4 and 5. Like this, U8. Oh no, yes, like this. Did I put 1? Yeah. So just like up here, we are getting a single item mutable pointer and coerce it to a single pointer pointing to an array of 1. Right, and we are making it optional as well, because down here it's expecting it to be optional. Okay, let's go to number 62. Remember using if-else statements as expressions like this? Yeah, yeah, I spent quite some time to make it multi-line and then I learned about blocks. Zig also lets you use for and while loops as expressions. Like return for functions, you can return a value from a loop block with break. Yeah, this I learned. But what value is returned from a loop if a break statement is never reached? We need a default expression. Thankfully, Zig loops also have else clauses. This is just like Python. As you might have guessed, the else clause is evaluated when 1, a while condition becomes false, or 2, a for loop runs out of items. Okay. Yeah. So if I have a range, I'm iterating through them and I finish without breaking, it will run else. And also if for whatever reason the condition I'm looking for, like I less than 5, then the same happens. If you do not provide an else clause, an empty one will be provided for you. I need to reduce my music sound, it's a little bit annoying. Yeah, this is better. I'm going to increase it a little bit on the stream. Yeah. If you do not provide an else clause, an empty one will be provided for you, which will evaluate the void type to the void type, which is probably not what you want. So consider the else clause essential when using loops as expression. This will be implicit else void. Yeah, because the type is defined U8 and that's not what I want. With that in mind, see if you can fix the problem with this program. Don't void, yeah, that's the error it's providing for lang. Yeah, let's find the first language with a 3-letter name and return it from the for loop. Okay, for lang, in langs, if lang break lang, else Uh, what should I put? Break none? Break expression outside loop. Wasn't this a syntax? Oh, it was like else none. It's null. None is Python. And then the go, yep, that passed. Even though the program was correct, it was raising an error because the type of void here wasn't matching this const u8, which is optional. Okay, let's do 63. Loop bodies are blocks, which are also expressions. We've seen how they can be used to evaluate and return values. To further expand on this concept, it turns out we can also give names to blocks by applying a label. Once you give a block a label, you can use break to exit from that block. Okay. As we've just learned, you can return a value using a break statement. Does that mean you can return a value from any labeled block? Yes, it does. Labels can also be used with loops. Being able to break out of nested loops at a specific level is one of those things that you won't use every day, but when the time comes, it's incredibly convenient. Being able to return a value from an inner loop is sometimes so handy it almost feels like cheating. Okay, and can help you avoid creating a lot of temporary variables. Yeah. In the above example, the break exists from outer loop labeled toLoop and returns the value 2. The else clause is attached to the outer toLoop and would be evaluated if the loop somehow ended without the break having been called. Okay, finally, you can also use block labels with the continuous statement as well. Yeah. We have print, as mentioned before. We'll soon understand why these two numbers don't need explicit types. Hang in there, Roger. We have food struct. The error I'm getting is on line 136. This is a huge program. Okay. We have chili, we have menu, and that is the name and ingredients list, which is a number. Oh, this size of ingredients is a number, but requires based on this table. So if 1 is true, it means mac and cheese are required. Okay. Welcome to Cafeteria USA. Choose your favorite ingredients and we'll produce a delicious meal. Cafeteria customer note. Not all ingredients combinations make a meal. The default meal is macaroni and cheese. Software developer note. Hard-coding the ingredient numbers based on array position will be fine for our tiny example, but it would be downright criminal in a real-world application. Good. Wanted integrations. Wanted ingredients. Chili and cheese. look at each food on the menu. Yeah, a for loop, we are labeling it for menu food. Now look at each required ingredient for the food. Yeah, we are indexing. Here we are making sure it's returning a slice. It's not an index. That's why. Yeah, it's a U size. This ingredient isn't required, so skip. Wait a minute, what's happening here? Here we are doing required. Okay, then this is Boolean. Ah, this is index. But the name is confusing. Required ingredients. See if the customer wanted this ingredient. Remember that wanted will be the index number of the ingredient based on its position in the ingredient list for each customer. Okay, that's basically it. Yeah, it's a bad name for this variable. Basically, this is the index of this array, right? And then this wanted means 0 chili and 3 cheese are required. Okay, based on the table above. And then const found. If not found, continue. If found, break true, else false. Okay. If we get this far, the required ingredients were all wanted for this food. Please return this food from the loop. Oops, we forgot to return mac and cheese as a default food when requested. Okay. First, I need to we have a for loop. If we get this far, should we just do break for loop and then menu 0? No, this didn't work. Okay, here I'm going to return food, that's the deal. And then else return food menu 0. This is how it should be. Yes, this makes sense. So here I wanted to return the food, meaning the required ingredients were all wanted for this food. Okay. Else return the default food. So let's mark these 3 exercises, and 61, 62, and 63 all solved. Let's go for 64. Built-in. The Z compiler provides built-in functions. You've already gotten used to seeing an at import at the top of every Zigling exercise. We've also seen at initcast in number 16 and 58, and int from enum in 36. Built-ins are special because they are intrinsic to the Zig language itself, as opposed to being provided in the standard library. They are also special because they can provide functionality that is only possible with the help from the compiler, such as the introspection, the ability to examine type properties from within a program. Zig contains over 100 built-in functions. We are certainly not going to cover them all, but we can look at some interesting ones. Before we begin, know that many built-in functions have parameters marked as Comptime. It's probably fairly clear what we mean when we say that these parameters need to be known at compile time, but rest assured, we will be doing the Comptime subject real justice soon. Okay, we have this print statement, we have some question marks, and then we have beautiful big function. Okay, the second built-in alphabetically is add with overflow. A and B, which returns a struct. The return value is a tuple with the result and a possible overflow bit. Let's try it with a tiny 4-bit integer size to make it clear. Okay. Check out our fancy formatting. Means print as a binary number, 0 pad, right aligned 4 digits. The print below will produce. Okay. Let's make sense of this answer. The value of B in decimal is 5. Let's add 5 to A, but go one by one and see where it overflows. So here we add to 1, and then it becomes 10. We move 1. This is no overflow here, no overflow here. Here we will have an overflow. True, the real number is and then again add false. Okay, in the last 2 lines the value of A is corrupted because there was an overflow in line 3, but the operation of line 4 and 5 themselves do not overflow. There is a difference between a value that overflowed at some point and is now corrupted, a single operation that overflows and maybe causes subsequent errors. In practice, we usually notice the overflowed value first and have to work our way backward to the operation that caused the overflow. If there was no overflow at all while adding 5 to A, what value would my result hold? The answer is unexpected result. What's happening here? If if there was no overflow at all while adding 5 to A, we have 1, 2, 4, this is 5, B, and then for A we have 8, 4, 13. If no overflow was happening, it means that 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1. I made a mistake, right? Try once more. 1, 1, 0, 1, come down. 1, 1, 0, 1. And then like this. And then here I have 1, 2, 4, 8, 16, which is 18, 5, 13. Yeah, correct. And then should I put 0, B, 1, 0, 0, 1, 0 here? Here's a fun one. If you can fix this attempt to use this built-in to reverse the bit of an U8. Yeah, LSP was helping, but here there was not much of an error, right? I hate it why it cannot go to the description of this function, but in general it seems like this one was expecting only one input and we were passing 2 to it. So number 64 also resolved. Zig has built-ins for mathematical operations such as square root, exponential, sinus, cosine, and stuff like that, and lots of typecasting operations such as pointer from integer and stuff like that. Spending part of a rainy day skimming through the complete list of built-ins in the official Zig documentation wouldn't be a bad use of your time. There are some seriously cool features in there. Check at call, compile log, embed file, and src. I'm going to put you here as well, 65. And then for now, we are going to complete our examination of built-ins by exploring just 3 of Zig's many introspection abilities. 1. This type returns the innermost struct, enum, or union that a function call is inside. Okay. TypeInfo that returns the built-in type, returns information about any type in a data structure which will contain different information depending on which type you are examining. Okay, and TypeOf returns the type common to all input parameters, each of which may be any expression. The type is resolved using the same pure type resolution process the compiler itself uses when inferring type. Notice how the two functions which return types start with uppercase letter. This is a standard naming practice in Zig. Okay, so if a function is returning a type, the standard is saying to make it capital letter first. Okay. Narcissus. Me. Narcissus. Myself. Echo. Alas. Poor echo. Okay. Fetch the most beautiful type. This, and this is going to return the inner type of the closest struct or inhabitants, so it would be itself. Oops, we cannot leave the me and myself fields undefined. Please set them here. Okay, we have another. Oh dear, we seem to have done something wrong when calling this function. We called it as a method, which would work if it had a self parameter, but it doesn't. See above. The fix for this is very subtle, but it makes a big difference. Fetch the most beautiful type. Now we print a pithy statement about Narcissus. Okay. His final words as he was looking in those waters he habitually washed were these: Alas, my beloved boy, Wayne. The place gave every word back in reply. He cried farewell, and echo called farewell. OVD. Okay. Struct field array. TypeInfo. Fields is a slice of a struct field. Here's the declaration. And please complete these if statements so the field name will not be printed if the field is of type void. Which is a 0-bit type that takes up no space at all. Okay, we have fields already. like this. Unable to resolve Comptime value. So how was it? It was like this, and then this, right? This was the only original definition. So we cannot call this directly, right? And then it's returning type, which means the arguments should be available in Comptime. Can I do why this doesn't work? What is the error here? Parameter type declared here, unable to resolve Comptime value. Or one more thing that I can do. Can I do type no field or member function fetch must be usable type? Oh, if you remember, it should have been defined as public, right? No, it's not a typo. Hmm. First it was beautiful. So seem to have done something wrong when calling this function. We called it as a method, which would work if it had a self parameter, but it doesn't. To fix this, to fix for this is very subtle, but it makes a big difference. So I'm going to copy this and ask gptel start a new one, or yeah, the previous one works. I have the following function. But after initialization, I can't call fetch the beautiful. Is a static method, no self parameter, but you are trying to call it as an instance of a method. Call static method on the type. This won't work. Okay. So here, this worked, but I had it public. Should I keep it public? No, it's unnecessary to have it public. Okay, so since it doesn't have a self, it's a static method. That makes sense, right? It doesn't have access to its body. But the return type here is this, has access to this type. So it returns the type of this struct, which is good. And if I want to make it dynamic, I can assign self to it and do it like this, or do this here. Okay. Okay. It was a complex one, but thanks to Claude, I learned about this one as well. And then here in the definition, it's adding this example. Okay. Why this happens without self, Zig treats it as a namespace function. With self, seems like, okay, that's probably it's going to admit it, right? That's something I know. I wanted to ask about if pub is necessary or not, and I don't trust LLM in that regard yet enough, because sometimes it has false positive. If I have such a question, I need to check the documentation. But for now, I think we proved it, right? Even without pub in a struct, the method would be accessible. Let's do 66. Compile time is a program's environment while it's being compiled. In contrast, runtime is the environment while the compiled program is executing, traditionally as a machine code on a hardware CPU. Errors make an easy example. Compile time error caught by the compiler, usually resulting in a message to the programmer. Runtime error, either caught by the running program itself or by the host hardware or operating system, could be gracefully caught and handled, or could cause the computer to crash or halt and catch fire. All compiled languages must perform a certain amount of logic at compile time in order to analyze the code, maintain a table of symbols such as variable and functions, etc. Optimizing compilers can also figure out how much of a program can be pre-computed or inlined at compile time to make the resulting program more efficient. Smart compilers can even unroll loops, turning their logic into a fast linear sequence of statements at the usually very slight expense of the increased size of the repeated code. Zig takes these concepts further by making this optimization an integral part of the language itself. What is the error here? Variable of type combinate must be const or comptime. All numeric literals in Zig are type comptime int or comptime float. They are of arbitrary size, as big or little as you need. Notice how we don't have to specify a size like U8, I32, or F64 when we assign identifiers immutably with const. When we use these identifiers in our program, the values are inserted at compile time into the executable code. The identifiers const int and const float don't exist in our compiled application. Okay, but something changes when we assign the exact same values to identifiers mutably with var. The literals are still comptime int and comptime float, but we wish to assign them to identifiers which are mutable at runtime. To be mutable at runtime, these identifiers must refer to areas of memory. In order to refer to areas of memory, Zig must know exactly how much memory to reserve for these values. Therefore, it follows that we just specify numeric types with specific sizes. The comptime numbers will be coerced if they'll fit to specify the size 32-bit. Okay, we can change what is stored at the area set aside for var int and var float in the running compiled program. To modify this variable at runtime, it must be given an explicit fixed size numeric type. U16 and F16. Number 66. One of them U32 and F32. We can change what is stored. Yeah, bonus. Now that we are familiar with these built-ins, we can also inspect the types to see what they are. No guessing needed. Yeah. And then there was a print statement somewhere. I'm wondering where does it print it then? Zig, or nosy eye. Zig, run, exercise, 66. Oh, there is a second line maybe. Or add next slash and here. Yeah. Const int is uptime. Yeah. Okay, Roger. Okay, I think that is it for today. I wish that I could reach out to a round number, but 66 is also round enough for today. Okay, thank you all. Please feel free to leave a comment if you see I missed something or I need to check out something to learn better or deeper these concepts that we covered today. I would appreciate it. And yeah, that's it. Thank you all.